Welcome to another amazing video by Miss Hewlin. Today's lesson is number 5 and can be found in your textbook in section 8.1. So today we're going to look at the properties of acids and bases. This whole chapter will be designed around acids and bases, so we do have to go back to a little bit of stuff we learned in grade 10. Today we're going to look at two different theories, the first theory being the Arrhenius theory. So in this theory, it states that an acid dissociates in water. If you guys don't remember what the word dissociate means, it means it breaks up into its specific ions. So an acid dissociates in water to form hydroxide ions. So we're going to underline that because it's pretty important. So for example, hydrochloric acid and sulfuric acid, they would dissociate and produce hydrogen ions, letting it be known that it is an acid. A base also dissociates in water to form hydroxide ions. So we'll do a little underline there. So for example, we have sodium hydroxide and potassium hydroxide, which are very strong bases. And if you were to dissolve them in water, what would happen is you would form hydroxide ions in the water. Different combinations of strong acids, we're only focusing on strong acids and strong bases right now, they will always react with the same exothermic result. So let's look at an example here. If we took hydrochloric acid and mixed that with sodium hydroxide, our products would be sodium chloride, which we all know is salt, and our other product would be water. Now going back to what we learned in grade 11, we learned how to break down total ionic equations and net ionic equations. So, lucky for you, because I'm sure you don't remember, I've already done it for you. So if we take hydrochloric acid, anything that has the state aqueous, it can be divided into its respective ions. So if we take hydrochloric acid and we split it up into its ions, we get hydrogen ion and a chlorine ion. We can do the same thing for sodium hydroxide, break it up into its respective ions, and we get sodium ion and a hydroxide ion. We then get sodium ion and chlorine ion if we break up the salt. But if you notice here, the state of water here is liquid, so we cannot break it up into its respective ions. The next step was to always cancel out anything that's the same on both sides. So hence we've crossed off the chlorine ion and the sodium ion. We then, in order to make our net ionic equation, we write down what's left over. So we have a hydrogen ion plus a hydroxide ion will yield us water. So no matter what, if you mix a strong acid and a strong base, the reaction that's taking place is the production of water. Everything else is just floating around as ions and no reaction is taking place with those ones. However, the hydrogen is linking up with those free hydroxide ions and creating water. This is an endothermic reaction that releases 56 kilojoules of heat. So really, if we were to look at this in a container, it would look like this. So as soon as you mix the hydrochloric acid into their water, it starts to split up into its ions. Same thing with the sodium hydroxide. And I mean, there would be tons of these, but I'm just doing it really big for our demonstration. So what would happen is the sodium and chlorine ions would continuously float around, and then instead of the hydrogen and the hydroxide ions floating around, we would be left with them linking up together. So this would now join with this, and you'd be left with water. So that's the Arrhenius theory. But along came the Bronsted-Lowry theory that kind of disproved the Arrhenius theory. There are a lot of problems with the Arrhenius theory. So Bronsted-Lowry came up with a theory that an acid is actually a proton donor. And you need to keep this straight. An acid is a proton donor. And therefore, a base would be considered to be a proton acceptor. Okay, the Bronsted-Lowry theory stated that there is no such thing as actual hydrogen ions that float around, but instead they actually react with the water that's already there, creating something called a hydronium ion. So that would be this right here, the H3O+. I'm actually going to write the name of that one. So that would be called a hydronium ion. so literally if we can look at the same image as above, we can draw out the same sort of idea. So if we look right here, we'll draw the exact same thing. So instead, there's also water molecules that are around. We still have those free, let's say free agents floating around. This hydrogen ion is going to actually link up with the water, which then in turn creates our hydronium ion. See, obviously it carries a positive charge because the water was neutral to begin with, picked up a proton, so it picked up another positive charge, so that's why it's H3O+. Your goal for today's task when you go to do your homework is actually to link up conjugated pairs. So if you look at the example below here, on the left-hand side here we have acetic acid. Water is very special in the fact that it can be a base in certain reactions and can be an acid in other reactions. So in this case, water is acting as a base. So if you look at the acetic acid, you'll see that there is a hydrogen on the end, giving away that it's an acid. Plus, if you look up the name of it, it's called acetic acid. And what happens is this hydrogen, once these two react, the hydrogen is donated from the acid to the base. So if you look after the arrows at our products, you'll see that that water now has turned into a hydronium ion because it has accepted the proton. Whereas acetic acid now has lost that hydrogen and we're left with a negative charge because it's lost a positive. So we have one extra negative, meaning we need to have a negative charge up top. So your goal is to link up conjugated pairs. So we know that this is an acid and this is a base. Acids will always link up with conjugated bases. So literally it's the exact same thing but minus a hydrogen. Because obviously acids are going to donate those hydrogens away. So here, I mean it's already listed for you, but these two will be conjugated pairs. Conjugated acid matches up with the conjugated base. Water, we know by looking at it, has accepted a proton, which means that it's a base. So a base will always match up with a conjugated acid. So you'll see here, base matching up with that conjugated acid. And that's all you have to do. You need to be able to write up the conjugated pairs. So we'll do a couple examples in a couple of minutes. Another thing that you guys need to take into consideration is the strength of acids and bases. Today we've been focusing on strong acids, and then over the next couple of days we're going to look at weak acids and bases. For a strong acid or base, they will completely dissociate in water. About 99% of it will dissociate. So that means if we take hydrochloric acid and we put it in water, about 99% of it will break up into its respective ions. Okay? So therefore, obviously, hydronium ions will be produced and hydroxide ions will produce if we're looking at a strong base. So because 99% of it actually dissociates, the concentration of our hydronium ions or the concentration of our hydroxide ions is actually equal to the concentration of the strong acid or the strong base. So basically, if you wanted to rewrite this to make sense for you, we would say concentration. So if we know what the concentration of our hydronium ion is, so say that was given in a question, and it asks you for the concentration of the strong acid, you'll know that those are exactly the same. That's what we're talking about here. So if you're given one of those two, you know both, because they are exactly the same. You do need to know some strong acids and bases through memory. So you might have a question on your test that would say, which of the following is a strong acid, which of the following is a strong base. So here is a list of the strong acids. So you'll notice just focusing in on the first three there. So these ones, you'll notice that they all contain a hydrogen. That gives it away that it's an acid. And then you have chlorine, bromine, and iodine. All three of those can be found in group 7 on the periodic table. So then you know that anytime you have a hydrogen matched up with an element in group 7, it's going to be a strong acid. The only one that is not considered to be a strong acid, I don't know if you want to make a note somewhere, is when hydrogen matches up with fluorine is not considered to be a strong acid. So everything else in group 7 is a strong acid except for hydrogen fluoride. The other ones you'll just have to do for memory, but we have sulfuric acid. We've dealt with that a couple of times in the lab. And we have nitric acid, hydrochloric acid, and hyperchloric acid. So you'll see it's just gained one oxygen. So it's exactly the same as the previous one, but it's gained an oxygen. So keep those ones in mind. Do something to help you remember it. The second one we're looking at strong bases, so something that gives it away that it's a base to begin with, is that OH, so that hydroxide group. If you notice the first two right here, we have sodium and potassium. Sodium and potassium can be found in group 1 on the periodic table. So usually you can think of if it's found in group 1 and it's matched up with hydroxide, chances are that it is a strong base. If you look at the second two, we have calcium and barium that is matched up with a hydroxide ion. You'll notice that calcium and barium are found in group 2. So elements that are found in group 1 and 2, chances are if they're matched up with a hydroxide ion, they're considered to be a strong base. So let's just put a little memory there that anything group 1 and 2. The difference between a strong acid versus a weak acid is that weak acids or bases only slightly dissociate in water. So remember before I was saying that 99% of it will break up? Well, if you take a weak acid in water, it will basically, barely any of it will break up into its respective ions, only about 1% of it will, making it a weak acid. So you still have that hydronium ion floating around, but it's not as much as you would find in a strong acid. Okay, so let's do some examples together. So this is on page 382. It's question number 4. So we're going to look at A first. So we have hydrogen sulfide plus ammonia is going to give you ammonium. And then you're going to have, again, that hydrogen sulfide, but now we've lost that hydrogen. We have a negative charge. So we need to first figure out which one is the acid and which one's the base. And in order to do that, we need to compare the one of them before to the one afterwards and decide who accepted a proton and who donated the proton. So if we look here before anything happened, we had 2 hydrogens, and then afterwards we only have 1. Meaning that this group of elements actually gave away a hydrogen, making it a proton donor. And we know that if we go back from above, we know that a proton donor is considered to be an acid. So we're going to write an acid here. Usually if one's an acid, the other one is probably the base. But we'll look to make sure that it is a proton acceptor. So we see that we have ammonia before. We only had 3 hydrogens, and now we've moved up to 4 hydrogens. So that base has accepted that proton that was given from the acid and now increased the amount of hydrogens. So therefore, it's a proton acceptor, making it the base. We know that acids will always match up with conjugated bases. So we can say that this is a conjugated base. And we can say that these two are conjugated pairs. We know that a base matches up with a conjugated acid, so we can say that ammonia, and I'm just going to put C for conjugated, is a conjugated acid. Conjugated acids link up with bases, so we can put these two together and say that they are conjugated pairs. And that's it. That's all you'd have to do for that question. So let's do the second one together. So we have sulfuric acid that is reacting with water. And we end up with hydronium ion and that sulfuric acid minus that one hydrogen. So we see here we started out with 2 hydrogen, and now we have 1, meaning that the proton was donated. If we have a proton donor, that's considered to be an acid. Here we have 2 hydrogens, and on the other side we now have 3. So that water has gained a hydrogen, or we could say accepted a hydrogen, making it a base. We know that acids will always link up with conjugated bases, so we can call this the conjugated base. And we can also say that these two are conjugated pairs. We know that bases always match up with conjugated acids, so we can say that this is a conjugated acid. These two would match up, and we would consider those to be conjugated pairs. And that's it for today's lesson. Tomorrow we're going to look in a little bit more depth into weak acids and bases, but make sure that you do have those strong acids and bases memorized, because you will need to know them for the test. Okay, thanks. See you later.